Hi everyone, my name is Maria. I'm happy to present our results for this shared task on behalf of Andrei Kutuzov and Alice Plum, my colleagues who collaborated in the project. We have tried two approaches to solve this task, and the first one outperforms the second. My talk is structured in a less conventional manner. I will first present our best performing approach and then move on to less successful strategies, so you don't have to wait till the end of the talk to get to the core of it. I will round up by providing some insights into the performance of our algorithms by doing some error analysis. The task of integrating new items into an existing taxonomy seems to usually involve 2 or 3 steps. First, one needs to select a way to represent words, and traditionally they would use either explicit properties of items such as substring information or rely on automatically induced features within one of the word embedding approaches. Secondly, a system would generate a candidate list. If the candidates on these lists are not synset IDs directly, but rather hypernym words, you will have to suffer through matching the hypernym words and the expected synset IDs. We have considered most of these approaches, and unfortunately not only theoretically but also experimentally, and our experience shows that the more steps there are in a strategy, the lower the performance. Our best performing algorithm involves 2 steps. First, we represent words, and then we predict synset IDs directly. The specificity of the first step is that we train custom word-to-vec embeddings that have vectors for most of the multi-words in the taxonomy. We noticed that almost 60% of nouns and 50% of verbs are multi-word expressions in the Russian WordNet. Besides, 20% of synsets have no unigram lemmas. It means that in the strategies that rely on standard word embeddings, which have no multi-word expression support, these synsets are inaccessible for prediction. To produce our custom embedding model, we have collected a huge Russian corpus, which counts almost 9 billion tokens after preprocessing. The corpus was tagged with UDPipe, and we have glued together parts of multi-word expressions extracted from Russian WordNet in this corpus. We have extracted around 40,000 noun phrases and 12,000 verb phrases, and rendered them as single tokens like the ones shown in the slides. This corpus was used to train standard embeddings in the continuous bag of word variant of the continuous bag of word variant. And while our major aim was to represent as many items as possible, we have used a very generous vocabulary limit in terms of the minimum frequency for items that received vectors, and we have set this threshold to 60. The second step in our strategy is a multi-class classifier. It is trained on all hyponym words paired with the respective hyponym synsets IDs. In total, we get more than 74,000 observations. The number of clauses in this classification amounts to 4,000. We have introduced an arbitrary cutoff of 5, meaning that we have only considered synset IDs that are seen in the training data more than 5 times. The classifier is implemented as a shallow feed-forward network, which returns a probability distribution over all possible IDs. We return the top 10 most probable IDs for each input word, for each test word. In fact, the neural implementation is not key in this setup. We have experimented with non-neural approaches and received very similar results. In terms of mean average precision, this model returns 0.49, which earns us the 3rd place in the competition in the noun sub-track. And it compares well with the leader of the competition, who reports 0.55. However, this strategy is less effective on verbs. In this sub-track, we have received only 0.24 with a bigger lag with the best competitor, who reported 0.44 in the competition. To comment on the impact of our custom embeddings, we would say that the gain that we have seen amounts to half a decimal point in all settings for all test sets that we have tested on. The solution that I have just described is an elegant and straightforward approach that was suggested by Andrei Kutuzov. Probably it was a desperate attempt to see at least some positive results after laborious attempts associated with the previous strategy, with the first approach direction of research that we have attempted for this task. And now I'm turning to the description of projection learning, the alternative direction that in our experimenting was chronologically first. The idea behind the projection learning approach was to predict the hyponym vector given a hyponym vector. The predictions were made by a linear transformation matrix that was learned on all available hyponymy pairs. In what follows, I will describe 2 types of modifications of this baseline setup. First, there is a group of ideas that did yield some performance improvements. By improvements here, I mean the change in the mean average precision score located in the 2nd digit after the decimal point. The second group of ideas did not live up to our expectations, despite being seemingly being theoretically justified. The improvements include 3 things. First, it is a better choice of pre-trained embeddings. Secondly, the learning process can be optimized by introducing a regularization term. And thirdly, we had tried to refine our candidate list by introducing some rules for ordering. Speaking about the choice of embeddings, our results show that word-to-vec work better than fast text, even though fast text does not return out of vocabulary words. Embeddings trained on a tagged corpus performed better than those trained on a raw corpus, which is probably a common knowledge for morphologically rich languages. Then we have seen that continuous bag of words outperformed skipgram models. And finally, we have compared the performance of embeddings trained in the same settings across several available corpora. And for this task, we have seen that, and this setup, we have seen that a huge Iranium rusicum maximum performed better than all other corpora tried. The improvements that were associated with the projection learning stage of this approach showed that the regularization, the penalty for the system that returns vectors that are more similar to the synonyms of the input word worked better, outperformed the alternative strategy to introduce a penalty for the output vectors that are similar to the input vectors. Then Hurst patterns also were successful. We have seen the difference for the systems that were scored on the default output candidate lists and those that used some refinement of those default candidate lists. Using Hurst patterns was contingent on introducing empirical thresholds for the number of items that were allowed to be reordered and for the number of items that could be considered as replacement. In our setup, these thresholds were 50 by 25. Then with the huge corpus that we constructed by concatenating 4 big Russian corpora, out of vocabulary words were no longer a problem. I had to edit out all the discussion of the failed attempts, but most of them had to do with refining the list of words that were returned as hyponyms. These included the use of cocurrence statistics, disambiguating hyponym IDs, then weeding out same level concepts, that is synonyms or co-hyponyms that occurred on the candidate list, etc. This slide has the comparative results for the successful attempts. The analysis of the numbers in this table can be summarized as follows. The gains, all of them in the second decimal digit, were seen for multi-word embeddings against the best performing Iranian vectors. Then we have seen the gains from using negative sampling on synonyms, and the Hurst patterns gave us a very small gain even in the third digit. Now I have presented our best system and the outcomes of some experiments within this project. It seems that I do not have the time to go into detail on the error analysis, and I do not have the heart to throw out my examples, so I'll just quickly skip through a couple of slides to go to the summary of the error analysis. I've arranged the negative factors that affected the performance of the projection learning approach in the order of importance. First, the major issue of this approach seems to be poor quality of the predicted hypernym vectors. It is especially obvious in the examples like Anisovka, where instead of the alcoholic beverage, the hypernyms are related to have a geographical interpretation of the word, like a town or a settlement or a region. The second issue with projection learning is the concept of similarity. The most similar items returned by cosine similarity measure are mostly third order hypernyms that are not accepted as correct answers. The other two issues are related to polysemy. Especially treacherous is the polysemy of the predicted hypernym word. In these cases, we see the output flooded by the unrelated senses of the hypernym. For example, for words that denote any sort of instrument, the candidate list would have medical instruments, musical instruments, and other instruments there. The manual analysis of the classifier output is not that straightforward as in the previous case. I'm bringing up some of the typical examples that we have seen in our results. Many of them raise doubts about the training data. For example, the taxonomy thinks that carom billiards is only a type of strike in billiards. It does not accept any other answers as correct. However, the Russian Wikipedia defines carom billiards as a type of billiards, not only a strike, and therefore our predicted answers, a game and a sport, look very reasonable. Another example is a case of mess jacket. It is defined as a type of formal outfit, usually a military one. Our system correctly identifies it as a type of outdoor clothes. However, it struggles with getting the second hypernym right. It is the meaning of coat. Instead of coat, it returns a jacket. It seems that our system reflects the interpretations that are inherent in our corpus. So this type of example does not count as a plain error, as a true error. It is rather the matter of opinion. It's rather a disagreement rather than an error. This is only a small part of what I wanted to share, but I guess I have to stop now. Thank you for listening.